In this video, we're going to be looking at Le Chatelier's principle. Now, a lot of Le Chatelier's principle, particularly AS level, is very much the same as what you will have seen at GCSE. So, thankfully, there isn't a great deal of new stuff to add on in terms of the principle. So, you know, if you make a change to the conditions of the reaction, the equilibrium will shift to oppose that change. So I'm just going to run through a few little Le Chatelier based questions just to highlight some exam technique and just point out where some common mistakes are made. So one of the first ones I'm going to do here is essentially what the features are of a dynamic equilibrium, because this is something that is easily forgotten. Okay, you talk all about shifting left, shifting right, and how does this affect it, how does that affect it. Ultimately, you also need to remember what the actual features are. So a closed system is one, they give you that, so make sure you read the question. Some people will write closed system as the answer when it gives it you in the question, so just be aware here, you can't say closed system. You need to state any other feature. Now, the main features of a dynamic equilibrium, there's just two of them really. Closed system is one, and the other one is that the concentrations don't change. Okay, so the concentrations, that's for concs, do not change. That will be enough to get you a mark. As an alternative, okay, you could also write that the rate of the forwards reaction is the same as, which equals the backwards reaction. So that's what a dynamic equilibrium is. Okay, it's that point you get to where the concentrations are no longer changing and you have equal rates of reaction back and forwards in a closed system. So that's what makes something a dynamic equilibrium. And now we go on to the more complicated questions, which are essentially then, what happens if I do X? So in this case, they're heating the equilibrium mixture. So, just to be very clear here, temperature is going up. Predict how the composition of the equilibrium mixture changes on heating. So, in order to work this out, we go back up to our equation. It's an equilibrium and we're given a delta H. Now delta H is always for the forwards reaction. Okay, you'll always be given delta H for the forwards process, not the reverse. So that means that going forwards is minus 9 kilojoules per mole. Minus 9 kilojoules per mole means that the forwards reaction is exothermic. Now, based on conservation of energy principles, if the forwards reaction is minus 9, the backwards reaction must be plus 9. Okay, it's the same value. Okay, conservation of energy, you can't have more energy one way than the other. So backwards is endothermic to the point of plus 9. So exothermic is forwards, endothermic is backwards. So to answer the question then, we've got to just look at what we're doing. So we're increasing temperature. So that means if we increase the temperature, the equilibrium is going to do the opposite. So that means it's going to do whatever it can to lower the temperature. Now, to lower the temperature, what it was going to do, instead of giving out heat, which is exothermic, that would increase the temperature even more, it's going to take in the heat into the reaction to cool down the temperature. And so therefore, the reaction is going to shift into the endothermic direction. So for 2 marks, it says predict how the composition of equilibrium mixture changes. So if it says composition of equilibrium mixture, or something to that effect, you have to talk about the quantities. So what I mean by that is, we're saying it's going to shift to the left-hand side. What that means is more H2 and I2, less HI. That's the composition, that's how it's going to change. And the reason, so the second mark here is explaining the answer, is because forwards reaction is exothermic, so forwards is exo, backwards endo, And the equilibrium, I'm just going to write EQM for equilibrium, will shift to the left to reduce temperature, or to lower temperature. Just reduce T. There we go. And there's your 2 marks. Nice and straightforward. Nothing too complicated here. It's just about highlighting what's your exothermic route, what's your endothermic route, and doing the opposite of whatever it is that you're doing. So if I increase the temperature, it's going to go in the endothermic direction. If I decrease the temperature, it's going to go in the exothermic direction. Yes, this can change based on the reaction. It might be the exothermic is backwards and the endo is forwards, but that's something you have to figure out on a question by question basis. So next question then. Bridget, explain what an increase in pressure would have on the equilibrium. So pressure, alarm bell should be ringing here, because pressure only applies to gases. Okay, now in terms of pressure, you're going to be looking at the number of moles of gas on each side of the expression, and whichever side has more moles of gas obviously has, the pressure is going to affect which way it goes. So increasing pressure, for example, in this scenario, means that you are going to shift the equilibrium to whichever side decreases the pressure. And to decrease the pressure, you simply want less moles of gas. Less moles of gas means you've got fewer particles in the same space, which is less pressure. So that's why we have to count the moles of gas. If there's any solids present, we ignore them. You can't pressurize a solid. So let's have a look. So we've got 1 mole of H2 and 1 mole of I2 on the left-hand side. So 2 moles of gas on this side. And on the right-hand side, we also have 2 moles of gas. So that means we can't actually change the pressure. It doesn't matter which way the equilibrium shifts, there's still going to be 2 moles on either side. So that means that in terms of answering the question, the effect, and it does say if any in the question, there is no effect. Okay, and don't be afraid to write that if you think it's correct. Okay, there is no effect, and the reason being is just the same number of moles, same number of moles on both sides of equation. Or moles of reactant equals moles of product. Anything along that line gets you a marks. So there you go. Okay, if there was a disparity in the moles, if you had more moles on one side than the other, then the equilibrium would have shifted to whichever side had the fewest moles. But in this case, that's not important, that doesn't matter. So, moving on then. Another equation, different idea here, but same principle really. This is 3 marks. It says high pressures and low temperatures give a maximum yield. Explain why. So, same as before then. Take a quick look at the equation. So we'll start with high pressures. We're just talking about pressures. So count the number of gaseous moles on each side. So we've got 1 CO2 and 3 H2. So 4 on the left and only 2 on the right. If I increase the pressure, okay, so increasing P, we will shift to the side with fewest gaseous moles, so fewer moles of gas. Okay, which is the right side. That's one explanation. And if I decrease temperature, let's have a look at the delta H then. So delta H tells me that the forwards reaction is exothermic. The backwards reaction is endothermic. So if I want to push the reaction to the right-hand side, I need to lower the temperature, because by lowering the temperature, the equilibrium will shift to the right-hand side to give out more heat in order to raise that temperature back up again. So by decreasing temperature, we're going to shift to the exothermic, to the exo right-hand side to increase temperature. Okay, nice and straightforward. Okay, that's all you need to do. Okay, in terms of the Chatelier principle, it's just shifting to the left, shifting to the other, both shift to the right, because you've got a few moles of gas on the right-hand side for the pressure, and you've got the exothermic process is forwards for the temperature. Nice and straightforward. Now, this question always pops up. Always linked to the Chatelier. It's worth knowing an answer for this, just so you've got it in the back of your mind, 'cause it's always the same answer pretty much. Explain why the actual conditions are different. It's 2 marks, so 2 points to make. One about the pressure, one about the temperature. So, really, so massively important thing to remember. Okay, high pressure, high P. Okay, it's expensive and dangerous. Okay, so both of these things are prohibitive. So in industry, you're likely not going to use the biggest pressure you can because it is dangerous to do so. Okay, it's very dangerous and massively expensive. In terms of temperature, okay, whenever you lower the temperature of the reaction, yeah, that's cheap. However, you're going to have a very slow rate of reaction. Okay, so rate of reaction is important here. Okay, if you've got, if you're trying to produce this commercially, you're doing it at a really, really low temperature. Okay, the main problem you're going to run into is you're not going to produce product quickly enough. If you're not producing product quickly enough, obviously you might want to increase the temperature to make it faster at the expense of your percentage yield. So nice and straightforward, it's always the same answers. And the final one I'm going to quickly run through, again, this time it's slightly different, but it's the same thing really. They've given you colors instead. They've given you brown, they've given you colorless, reactants and products. Using Le Chatelier, how is it going to change things? So here we go. For part 1, it's got the gas mixture is compressed by pushing in the plunger of the gas syringe. So first part then, compressing the gas mixture. So let's take a look at our equilibrium. Count up the number of gaseous moles. So we've got, this is very easy, 2 on the left and 1 on the right. If I compress the gas mixture, that is essentially increasing pressure. What's going to happen? So it's going to go to whichever side has the fewest gaseous molecules, therefore it is going to shift to the right hand side. So equilibrium shifts right, and you can always say because fewer moles of gas. There's nothing wrong with explaining yourself as you go along. Of gas, and then you have to state how the appearance changes. Well, if it goes to the right hand side, it's going more colorless. So color change, okay, from brown to, I wouldn't say it's going to go completely colorless because you've got, obviously this is a slidey scale. The equilibrium will shift to the right for sure, but it's not going to go all the way over and get completely rid of everything. So I would say pale brown, or just say color change from brown to a paler brown / more colorless. Okay, so it loses its color. That's the idea. Okay, but don't just say it goes colorless because it's very unlikely to go completely colorless. The second one then, placed in a warm water bath. So that is essentially increasing temperature. That's a very bad thing. I don't know how I did that. But yeah, it's increasing temperature. So if I'm increasing temperature, we have to look at our exo-endo. So again, some negative ones. So exothermic along the top. Endo is going backwards. If I increase temperature, it's going to go to the endothermic side. So equilibrium is going to shift to the left. Okay, because it's the equilibrium shifts left because it's the endothermic side. Reduce temperature. And the color change is just going to get darker, isn't it? Okay. So the color turns darker brown. A darker brown. Nice and easy. So there you go. In terms of exam technique then, what like I said, I always write these things on the equations, and you can do this too. If if you get confused by this, just write above and below the equation which way is the exothermic, which way is the endothermic, how many moles of gas do you have. Always explain the Chatelier questions in terms of the equilibrium shifting right and left. So always say equilibrium shifts right. Don't just say it goes toward the reactants or goes towards the products. Use left and right. Be explicit. That way the examiner knows you know what you're talking about. And if it does ask for appearances, just take a look in the question. There might be colours to think about as well. In terms of compromise conditions, just remember, even though something might have a very good, might shift the equilibrium over to the right hand side, doesn't mean it's what you want to do, particularly if it leads to a very slow rate of reaction or it's expensive, such as high pressures. So there we go. Like I said, these questions are very, very similar. They don't change in their scope much. They very much ask the same thing, but it does get expanded on at A2. So a good understanding of this content now is really good for future success.